Well, good morning, everybody, or good evening, depending on where you are. Thanks for coming to this webinar, Everything You Need to Know About Data Visualization with PLS Toolbox and Solo. I'm Barry Wise, President of Eigenvector Research. Our Master of Ceremonies is our Scott Koch, who's our lead developer in software. And first, let me just say that I hope everybody is safe and healthy and not too bored. And this will give you a little bit of a respite, I suppose, a chance to do something else today. So this is how we do these. Everybody is automatically muted on entry. We don't use video. I'm just sharing my screen. As I mentioned, Scott will act as master of ceremonies. And we use the chat function to type in questions, and then Scott will relay them to me. So that's generally how we work. And please keep yourself muted. We really appreciate that, and communicate through the chat. So I thought long and hard about how to organize this, and it finally occurred to me the only reasonable way I could do it would be to organize it by different data sets, and each data set that I have has a different thing I like to show. First, though, I want to talk a little bit about setting up your data set object. And the data set object is our container for data sets. And it's key to being able to do a lot of visualization tricks later. And then I want to say a little brief word about PCA and PLS, and then I'll go on from there and use a number of different data sets, and each will show a few visualization tricks, and then we'll summarize. So first, the dataset object, or DSO as we call it. This is what one of our data sets looks like when you open it up in PLS Toolbox or Solo, and it shows you your data in data view. But the data set object has a place for everything, and you want to put everything in its place. If you do that, you'll be able to do a lot more later. The DSO keeps metadata that is associated with your data sets organized and accessible. And many visualization methods rely on metadata. And what do I mean by that? Well, those are things like axes that you plot your data against, either samples or variables, classes, and associated measurements. So the dataset object in this view, in data view, has your data matrix. So that matrix is the main part of your data set. But you also have, for instance, sample labels on it and variable labels. And with that, I'm going to skip for a moment over to MATLAB. And you know what I'm going to do? I'm going to downsize this for a minute and get it out of my way. And I'm going to load up a data set that we use a lot. Arch is a data set that is archaeological data. The samples are obsidian samples from known areas and from archaeological digs. The variables are the metal concentrations in these obsidian samples. And have just drug the file for Arch into our workspace browser. And now I'm going to just open that up in the dataset editor. So here's your dataset editor in data view, which I already showed. But if you want to start really putting information in this, then you would click on this tab, row labels here. And this is where all this is contained. In a couple of weeks, we're going to have a webinar on data import. For now, I just want to show you where it's contained. But this, for the rows, which are the samples in your data set typically, we've got sets of labels that go with them. You can have axis scales. I just put in a numerical 1 to the n scale, but you can also have scales like this one, which is a date and time stamp. here, I actually created this one sort of at random. This data set was taken in 1971, so that's why it says that. You can also have class variables here, and you can have multiple ones of those. Here we only have one, but those classes are where the samples came from. So that's the sample mode. We can also look at it in variable mode. Here's the column labels, and these are the elements that we have the concentrations of: iron, titanium, barium, etc. I can have an extra set of those in here. I wrote the full names out if we want to have the full names listed on things. You can have axis scales in here as well. I put in several. I put in also, for instance, atomic number of those elements. That might be interesting. Or atomic weight is in here. And also, I put one class set in here of element type, whether it was a transition metal, an alkali earth, or an alkali metal. And so that information then will be available later when we start working with this data set. Okay, that was all I really wanted to say about the data set object itself. I just wanted you to know, though, that there's a place for all this, and if you take the time to get this information into it, you can use it later when you're doing your visualizations. All right, I'm going to go back to my slides now, and I want to talk just briefly about PCA, PLS, etc. In this webinar, we're assuming that you're already familiar with common chemometric methods, including principal components analysis, partial least squares regression, PLS discriminant analysis, curve resolution, etc. But each of these is really a data visualization technique in its own right. They all provide dimensionality reduction. Typically, our data sets have a lot of variables, so they're a very high dimension. And since we're just used to living in 3 or 4 dimensions, then we need to have a way to reduce that down to some things that we can see. Each maximizes variance or covariance explained. They're linear and thus they're pretty easily interpretable. PCA in particular is a great data visualization technique because it spreads out the data. Capturing variance is actually just another way of saying that. PCA finds the views of your data, the projections that spread the data out the most and allow you to see the patterns in it. And it can be used to identify things that are the same, or if they're different, why they're different. But our subject is how to bring in even more info. We're already using PCA, for instance. What else can we bring in to get more information out of our data? So let's start doing a little bit of that. And I've got my arch data set in here already, and I'm going to go ahead and load this up in PCA. And this is our interface, our analysis interface as we call it. And I've got it in PCA mode. So the first thing we might want to do with a data set, of course, is plot it. And I can do that. I'll say plot data. This is the average sample in this data set. I can put my labels on this. So this is the average concentration of the elements in my samples here. But I might also want to see all of the data right here. So this is all of the data. You can begin to get an idea of the spread in it. But it might be actually nice to see it by classes. And I can turn on those classes. And the classes are the quarries that these things came out of. So now I've got my data where the symbols are according to what quarry each one of those came out of. I can actually put that on the plot. Here are the different areas that these came out of. They're called Canocti, Borax Lake, Sugar Hill, and Annandale. Class zeros are some unknowns that I have in here. could also change my plot type here to a line plot. If I do that, then it switches to lines. And now I can see already that I can see a split in this data according to where the samples came from. And so we always encourage people to start here. That is, plotting your data and adding class information to see if you begin to see structure in it. Here, for instance, I can tell that the anadel samples are high in iron and they're high in calcium. These blue samples, which are the sugar hill, tend to be quite low in calcium and low in iron. And if I actually zoom in here, I can see that even in these minor elements that are in lower concentration, I still see structure out here in this. Like my anadels are a little higher in manganese and a little lower in rubidium, for instance. Okay, so that's sort of our starting of plotting there. Let's go ahead and make ourselves a PCA model of this data set. 4 factors I just know from working with this data set is a good place to start. And let's go ahead and look at some scores plots. So here I just clicked on the icon for scores, which is our Erlenmeyer flask, and brought up a standard scores plot. Here's scores on the first versus second PC. And notice that these are colored by what class they are, in this case, where they came from. Well, that information was contained in the dataset object. That was one of the classes that we had for samples that are in there. And you can change what classes, what symbols you use for classes. And I had some questions about this the other day. And let me see. So classes, we can go to change symbols. This is sort of my favorite set, is that one that I created. But you can create your own sets, and that are colors that are pleasing to you. And in order to do that, if you do choose change symbols and then custom, you actually get an interface up here that allows you to pick every symbol and change its face color and its edge color here. And you can create a whole set of symbols that you like. And especially you might have some instances where it makes sense to associate classes with different colors, etc. I'll also point out that we had a question from a user the other day about sample sets, or rather symbol sets that work for people that are colorblind. And so, for instance, I created a set here the other day that's based on the Perula color map that should be good, if I understand color blindness correctly, for people that are colorblind. And it's a set that doesn't have any red-green distinction in it. Instead, it's all based on a color palette that goes from yellows to greens to blues. And so that is a set, for instance, that might be good if you are working with people who are colorblind, and a significant fraction of the population actually is. Okay, so what else did I want to show you here? We have in here, here's my set for scores. I also want to show that some things I can do here in loadings. So these are my loadings for this model. I'm going to plot PC1 versus PC2. And I can put, of course, the names on my loadings. But there's also a tool that we like really well that's called color by. And I could, for instance, color these now by anything that I have an axis for. So for instance, I can click my color by bar over here, and I can now color these by, say, atomic number, and see if I see any patterns in that. I could do atomic weight there, since that's also in there. I don't see actually anything too interesting there, but it is nice to do it this way. Let me get rid of the color. I can choose to view the labels on this, or excuse me, the classes. I have element type in here. And my element types are whether they're an alkali earth, an alkali metal, or a transition metal. And so now I can actually see some things that are going on here in the chemistry. I've got a couple of elements here that are the alkali metals that group together. I've got a couple of my alkali earths, one sort of stray one here, and then the rest of these are transition metals. And so now I've added some information to the plot really about the chemistry going on here. And it might make really good sense here, in fact it does, that you get a couple of alkali metals that perform very similarly, whose concentration goes up and down together. And for instance, calcium and strontium we know are really chemically similar, so it's not surprising that they have similar loads here. All right, want to go back to my scores plots and show you a couple other things here that can be done. Another thing that is nice to do is to be able to view what the spread in these groups is. So up here in this icon, there's an option to put confidence ellipses on each of those. And so now you can really get an idea by looking at how spread out these classes really are. And it's interesting because when confidence ellipses are drawn, it takes into account how many samples are in the group. So this group here, which is the borax lake, I believe, is really spread out because not only does it have quite a bit of spread in it, but it actually has fewer samples in it than the other ones do. And so that gives a wider bound on the confidence interval on that. And this actually works in 3 dimensions as well. So we could add a third dimension to that and now see what these look like in 3D. And I always forget, MathWorks changed where they put some of the controls here, but we can rotate this around, and now you can really get a better idea of how these different classes of obsidian samples are related to each other.
Hey, I had a question, Barry.
Yeah.
When you're building a Simca model, would you get the same type of ellipses?
Well, I mean, this is sort of a representation of a Simca model, yes. So if you modeled each one of these classes individually, then essentially each one would have an ellipse like this around it. So I would say, yes, this is a sort of a visualization of a Simca model. All right. Oh, a couple of other things. Let me go back to a couple of other ways that you can show how samples are spread out. You can choose also to do spider plots are useful sometimes. It helps you actually for data sets that are kind of overlapped, find the center points of them and see the spread that way. Another way to do it is to do the border points and just find the edges of them. And again, when they're overlapped, and that helps you find the spread in the classes. One last one is to do points in sequence. And this actually connects them in the order in which they're in the data set. And that might tell you something about how things have drifted over time. Okay. All right, I'm going to I'm going to stop with Arch here now and bring up a new data set. So I'm going to close that. And now I'm going to go onto a data set that's become a favorite of ours, the NIR shootout data. This is from the near infrared diffuse reflectance meter, the Chambersburg one that they have every year. And we're going to make a quick PLS model here, and I'm going to show you a few things that you can do there. So I'll start up my partially squares interface. And I'm going to load some of this data into it. I'll load both the X and the Y. For the X, I want this one that's called Calibrate 1. And for the Y, I want this one that's called Calibrate Y. Why? Because we like to calibrate. And this data set is near infrared of pharmaceutical tablets. And we're going to make a model that predicts the assay value of the tablets, and it's diffuse reflectance data. Technically, I think it's diffuse transflectance data. I'm going to select what variable I'm going to model. I just want to model the assay 3 values, so I have that. But let's take a quick look at the data. So I'll say plot data. This is the average spectrum in this data set. And so here we see this is near infrared, so your variables are actually the wavelength in nanometers here. And we can see the whole data set if we click on data and the plot controls there. One of the things that, if you're familiar with this type of data, you can see is that a lot of the variance here is baseline offset that has to do with the scattering phenomena. And of course, scattering is a physical phenomena that doesn't really have anything to do with the chemistry. It has to do with particle size distributions. And so you get a baseline offset because of that. And we can look at this to see if we can find some effect of the assay value in here. So I'm going to use color by and select assay, and now this is colored by the assay value of the tablets. So the ones that have the highest assay values of active ingredient are the yellow ones, the lowest ones are the blue. We can see some differences that look to be due to the change in the assay value. Might also note that this is the Perula color map. This is the color map that is supposed to be friendly to color blindness. It's not personally one of my favorites. It's easy enough to change. You can, for instance, right click on the color bar there, and we can change that to jet, and I'll just say replot here. And now it's in this color map. And yeah, a lot of the distinctions there are red-green, so that's probably not very colorblind friendly.
Yeah, I was going to say that one of the participants posted a link in the chat with some additional information for developing color maps for colorblind.
Oh, good. Good.
We also had another question was about assigning class information for large data sets.
Okay, well, there's a couple of ways that you can do that. One is if it's already clustered, you can select samples and then set classes graphically of big groups of samples. You can also use some of our cluster analysis methods to automatically assign classes to it. If you have the class information available with part of your samples, you can load it into the data sets, and you don't have to do it by hand. You can read the files in. So that's 3 ways that can speed setting classes up on large data sets. Oh, okay. So I do know from working with this data set that the either end of it isn't very used to or very useful for modeling. So what I'm going to do is I'm going to select just part of this, and I'm going to then under the edit menu, I'm going to change my selection mode to X range, and then I'm going to do a selection. And I know from experience that this is good from about here to about here is the useful range in this data set. So I'm going to select that, and I'm going to say edit, include only the selection. So I'm going to only model on the part that I selected. And so we're going to work with that right there from about 1100 to about 1600. So I'll go ahead and close this. And I'm going to make a really quick and dirty PLS model here. And I'm just going to use mean centering for this. And I'll go ahead and make a model. And our first model here is going to be less than wonderful, but we'll work from there a bit. So I've made a model, just a simple two-factor model here to start. And you can see that this is my calibration curve here. I can put my stats on it if I like, show on the figure my error of calibration and my error of cross-validation. There's a fair amount of scatter in this. Well, that could be because I just did mean centering. So let's take a look at a couple of tricks to look at pre-processing data. Now, I'm going to set that aside. So we have a tool in here under pre-process. You can get to it either way here. Plot pre-processed data, XBlock. Okay. So this is actually what my data looks like right now. And when you just take this data set and you mean center it. So I'm going to color this by the Y block again and color it by assay. And you can see that, yeah, the data kind of sorts itself by assay a little bit, but it isn't awesome. So let's instead think about what we would do for to improve the pre-processing. And here's a trick I use from time to time. This is our pre-processing window. Here's all the methods that we could pre-process with, and here's what we're actually using. So I'm going to start by removing all pre-processing, and then I'm going to say OK. And when I do that, this window updates to the data without any pre-processing. Now what I want to do is I'm going to add my pre-processing steps here one at a time. So go back and edit my pre-processing again. Well, the first thing that I want to try is what does a multiplicative scatter correction do to this data? That's a type of normalization here, and I'm going to go ahead and add that. And I can actually look at this in this window. This shows what it does. It takes my spectra from this, removes a lot of the baseline offset, and creates this. If I close this window, it'll update this plot here, which is a little nicer. My plot over here, I'm using color by, so I've got the assay information in here. And I can see now that once I do a scatter correction, that my data is starting to line up better by assay value. Okay, well, how about a derivative? A derivative might help this data set. So I'm going to go back, add a derivative in. I can add that. And I'm just using the standard default methods. And now my data set goes from this to that. But again, I want to see what it looks like back here in my preprocessed data using the color by. And so that's what it looks like after taking the derivative. And now I'm going to take one more step and I'll put the mean centering back in. So one last time, I'll edit this and I'll add the mean centering to it again, which is down here. Add, make sure it's in the right order. I want that to go down. I actually want multiplicative scatter correction to go up. And I'll say OK. And so now this is what this data set looks like before it actually hits the PLS model. And it's colored by assay value. And you can just tell by looking at this that this model stands a pretty good chance of working because I have a lot of features that line up with the assay value using this set of preprocessing. So that's one of the things that I encourage, is to use visualization to see if your preprocessing is doing what you think it's doing and looks like it's going to be something that's effective.
Hey Barry, we had a question. What if you were had a multi-Y calibration?
Well, you can color this by any of those. In fact, like here, I could choose to, maybe I want to model assay value here instead, or not, like weight, if I wanted to model weight. And I can see how it looks on that. Another trick that we do, which doesn't look like it has a lot to do with weight there, maybe just a little bit. That is, though, one of the tricks that we do in like classical least squares models is color by the different analytes your raw spectra to help you find the features in them that you're going to be modeling on. So that's a really good help in that. I don't know if that answers your question.
Well, yeah, I think it does. And you could also open multiple windows.
That's true. I hadn't thought of that. All right. So that's a good way to look at how preprocessing affects data. I'm going to close that. I'm going to make a new model here and get that going. And now I just wanted to point out a couple of other things. One is that now in our scores plots, here's my scores on the first two latent variables. Well, I can take this and I can color that also by assay value. So now here's the plot colored by assay value. And you can see, as you might expect, that first latent variable lines up with assay value pretty well. So that's not too much of a surprise. But a question here might be, well, why do I get the spread up and down in this data? Does that have to do with something else? Well, let's take a look. So I'm going to instead color this now by weight. And when you color by weight, you discover that it appears that the spread up and down has at least something to do with the weight of the tablet. And that suggests to me that there's a geometry or a density issue that's causing the scatter that goes up and down. And it's actually even interesting to color this one by the hardness, and you actually even see some trends in the hardness here, where I could see the hardest tablets are up here and the softer ones are here. So in general, there's a relationship apparently between hardness and assay value, but also with that weight parameter. So these are really good ways to find out some things that are going on in your data. And one last thing here I wanted to do is show you that you can select points in any plot here. I've got some obvious outliers, and I'm going to go ahead and select those. And now, if I go into my other plots, here they are. So those samples that I just selected that are really off my regression line quite a ways, well, I just found out some things about them now. They don't have particularly interesting scores. They don't have particularly high leverage. They just have high Y residuals. They don't have large Q residuals. All this here is evidence that these samples probably just have bad reference values. And I've actually talked to the owner of this data set, Gary Ritchie, and yeah, that's most likely the problem here. So I can just edit those out. I could say exclude that selection. And now I can rebuild this model without them. And I'm on my way to making a considerably better model.
We had a couple more questions, some of the details about plotting. When you're using color by, you're plotting along an axis. Is there a way to plot along a shape axis, like a number of sides of a polygon for different symbols? I mean,
Yeah,
we don't.
are we talking about like rose plots or something like that?
Um, yeah, I think it would be just developing the symbol based on a color by value,
Mm-hmm.
and we don't have that, but it's an interesting idea.
Yeah.
Here's another question. After the plot is colored and a legend is generated, can I change the order of each group in the legend? I don't know that off the top of my head.
Um, you can, if they're classes, because you can edit the class lookup table and put it in any order that you want. As far as color by goes, that's always going to be in some monotonically increasing or decreasing, because color by is used on real values, whereas classes are essentially integers and you can rearrange them. So I don't know if that answers that, but if you choose classes instead, you can change that. I won't get into this now. There is all sorts of issues though with how you layer things, and we're going to do an example about that in a minute. I just wanted to show you one other quick thing here. This is a data set for I'm going to use in PLSDA. It's a metabolomics data set. It's essentially the lipid panel from patients before and after chemotherapy. And we're going to build a really quick PLSDA model here on this. And my classes here are the baseline. This is before chemotherapy, and then right before being operated on. And so those are my classes. And I'm going to make a really quick and dirty model here of this to see if we can separate patients from their lipid panel based on whether they've had chemo or not. There's a couple of missing data elements in this, and we'll replace them. And so here is my PLSDA model based on this. And in my scores here, this is how I've is my bottom is my predicted class here. I'm going to change that classes to something that's a little friendlier here. So change symbols to my Perula based, and hopefully that's a little better. Let me see. How many factors should I really have in this model? Actually, 7 is a better choice here, so I'm going to make 7. So 7-factor model. But what I just wanted to show here is there's a really nice visualization trick about distributions that you can use. So this is my prediction here as to whether this belongs in the baseline class or in the OP class here, BL or OP. And I can actually right click on points here, and one of the options for things to do is to make histograms. And I can make a histogram of my Y data, and that then shows as a histogram how my classes really overlap. And it's also a nice way to look at this in terms of, this is my cross-validated statistics. So this is real performance, as opposed to, I could put here the actual fit to the data and look at the distribution in that and do a plot of that, and you can see that in the fit we can separate them much better than we can in the cross-validated predictions. And so those histogram tools are really nice also. The other thing I wanted to point out is just if we're looking at loadings and we want to find important variables here, I'm going to just run down to the VIP statistics, the variable importance on prediction. These are discrete variables. Each one is the concentration of a different lipid. If you put the labels on here, this would be pretty busy. You don't really want to see all of them. But one visualization trick that you can use is I'm going to select just the big ones here, like that. So those, and put the labels on those. And so one visualization trick here is to select the interesting stuff, and then when you use labels, the labels will only show up on the stuff that you've selected, and that helps you see what's going on. Okay, I'm gonna close that one.
I had another question. Is it possible to show more than one class set in the pre-processing window when you're looking at when you show the plot? I think is it only the first set that's available there?
In the pre-processing window?
Yeah.
Yeah, boy, I don't know the answer to that one.
All right, I'll look it up and I'll post the answer in the chat.
Okay, I've got another data set here, and this is near-infrared spectra of foodstuffs. It was the challenge problem in the chemiometry conference from 2018, and I'm just going to do a little bit of PCA on this, because I just wanted to show you a couple of kind of handy things. In this data set, let's see, I'll just pre-process this. Oh boy, I'm trying to remember what's good in this data set. Actually, I'm going to do an MSC and a derivative in this. I know works pretty well too. Kind of typical near IR data. And I don't want to auto scale, I want to mean center. So let's mean center, add. And I could show this now. Yeah, okay. So, all right. So now I'll go ahead and make a PCA model of this. And the main reason I'm doing this is because it's kind of busy. Okay. So we get this scores plots here, and this is all of our different foodstuffs. And oh, I had renamed those at some point to what they actually were. So forgive me for that. But one of the issues that you get in plots like this is you get things covering each other up. And so what you can do is you can send groups to the back here. And so if I click on a group and then deselect it, it gets sent to the back. And so any group here that I click on, then an element of, then it winds up in the back of the plot. So that allows you to sort of see how the groups really lie, because you do have this problem where when the samples are put down, or when the classes are put down here, they're put down in groups of everything of one class, and they wind up being one on top of the other. And that makes that sort of hard to see. One of the things that you can do is you can change the size of the class symbols and make them smaller. That helps sometimes. But sometimes it's easiest to just send things to the back. And that lets you really see the structure in the groups on top. Another thing that you can do in this data set, I actually included as an axis in here the protein content of these. And these are all different foodstuffs. But here, because I put the protein content in here, I can actually use that. And to color them by, except for I think I just grabbed the wrong version of this, that I didn't put it in there because it's not on my list. But if I had that, I could use that too. Okay. Actually, let me do this. So if I load into the interface here, even though this is PCA, I can actually load in a Y block here and use it to color by. So here it is loaded up. And now that it's loaded, it'll be available in the color by. Load from Y block, protein, and now we're colored by protein here. And you can actually see that the different groups here are really generally different protein levels in this. And so that's a handy thing to be able to do too. All right. So I wanted to do just one quick example with PCA, and this data set here is an Excedrin tablet, and it's been cut in half and imaged with reflectance spectroscopy, and we can do PCA on that. And pre-process, I'm just going to mean center this. And it turns out a 5-component model describes this pretty well. And here now we can see the tablet. We're looking at the cross section of it and the scores on each component. And so image PCA is really nice for summarizing information. But it turns out that in some of these, we can really see the domains here pretty well of each thing that's in here. Turns out these right here are, I know, are actually the aspirin comes out. Uh, these here are the caffeine, and that really come out in this component. Well, when we're looking at these, we can actually then combine them into red, green, blue. And so this is now the first three PCs where the colors are assigned to red for the first PC, green for the second one, and blue for the third. And we can also increase the contrast in this so that we can see what's going on a little better. So now if I turn on auto contrast, that essentially spreads out the differences in the middle of the scale a little better so that we can see. You can actually do all five at once, and it interpolates the colors for the other. So Image PCA is a great way to visualize things, and by coloring them this way, you can really see the differences in things come out. And it may be, however, that you don't like the color gun order. So in particular, my PCs that look interesting here is 2's interesting, 3's interesting, 4's not, 5 is interesting. So I can choose to plot 1, 2, excuse me, and 5, and it gives me this plot. But what if I don't like that ordering of the colors here? So I can put my legend on. I'm using red, green, blue this way. If you go to the view command here and go to the settings, it turns out that there's a ton of settings that control things that the plots do. And that's everything from symbol size here to line style to line widths. There's information here about what it does with labels, and information's about class sets and what size. But the one that I want to look at here is in images. There's the color gun order, the image gun order, and you can change that. So now it's red, green, blue in that order, and I can switch that, for instance, to something completely different. I can start with the blue, and then red, and then green, and choose that setting and say OK. And now I get this representation of it. It may be that for your own particular problem, it makes sense, for instance, that the trees in it be green and the rocks be red, if you've got an image like that. So how you associate color with a particular feature can change the look and make it more sensible to look at.
Okay, hey Barry, we got a couple questions here.
Okay.
There's one about starting with data in Excel and then building up a data set. And I was just going to say that we'll be talking about that in our next webinar. It'll be almost exclusively about importing data and setting up data sets. So tune into that one for an answer there. We also had a few questions here. If you go back to one of the plots you had, if you know what your PCs are representing, can you rename them in the plot? That's in the legend.
Well, okay, I'm gonna show you a little bit of a hack here. I did an MCR model of this data set, and where and I actually do know what's what. So for instance, now in this model right here, I do know here uh, what is what, and I can put it on there. And so here it is actually assigned aspirin, acetaminophen, cellulose, caffeine, and another type of cellulose that's in this. So yeah, you can. It's to really get that to show up in the plots, you have to turn it into a classical least squares model and do that. We were fussing with that actually a little bit yesterday, trying to find an easier workaround for it. And so let me just say that it is possible, but the workaround for it's a little bit of a pain. I did want to show you this though, because now you really are visualizing this after having done a curve resolution model and assigned these to actual components. You know, this now isn't just the first component, that's actually aspirin concentration. And that's actually acetaminophen concentration. And that is actually the caffeine in this. And so that's really a true visualization of the chemical map of this. All right.
I had a question here.
Mm-hmm.
It's asking about the data set, if this data set is available somewhere. Or no, I'm sorry, the 2018 one.
The chemiometry one.
Yeah.
Yeah, and you can get it from them, but I tell you what is we'll put it on our website. I um, have a version of it where I also assigned the actual names to all the classes and whatever that I was supposed to be using today, but I missed. And we'll put that one up. It's a really nice data set to fiddle around with.
You know, and Neil mentioned that you can also save your loadings from the plot and then change the labels in the data set that is the result.
Right. Yep. Okay, I'm gonna leave with just do one quick example from just the slides here. So this is an example data set of SIMS depth profiling, where we have a surface here with what they call pinapam on it, which is poly N isopropyl acrylamide on a C3F6 surface on a silicon wafer. And so for every pixel here, we have a full mass spectra. That's how secondary ion mass spec works. But this has been depth profiled. And so we actually wound up with a data set in here that's 85 pixels by 85 pixels by 300 channels in the mass spec by 50 layers in this image. And we did curve resolution on this. And so here's an example of this is the curve resolution component for the bottom layer, the silicon layer. And my movie's been playing kind of herky-jerky when I've been doing this. But we can actually run through this, so you can look at this by slices here. And all of this was computed with curve resolution in our image analysis software, but I have to admit that I put this together using just straight MATLAB tools in order to create this visualization. But the really interesting part about doing this visualization was that we discovered that this actually is a data artifact in here, that we have areas with less signal that go up through here and they actually continue through the other layers. And we think it's actually an artifact of the way the SIM samples the surface. So by doing this particular visualization, we found out not only where the layers are and sort of how rough they are in between layers and issues like that, But we also found out something about the technique that was used to generate it and some issues with the sampling of the ion beam on the surface. It's kind of interesting. So, I mean, here's an example of essentially imaging a four-dimensional cube, x by y by z by spectra. Okay. So in summary, uh, first off, a properly prepared dataset object is really key to visualization. A DSO provides a place for multiple labels, multiple axes, multiple classes, and that info then creates all this extra stuff on your plots that really helps you figure out what's going on. And that includes plot symbols, uh, the ability to plot things against various axes or color by those axes. Um, that a lot of that comes out of the DSO. And of course, PCA, PLS, PLSDA, MCR are all really visualization techniques in their own right. So they each provide dimensionality reduction, and you can get that down to something that you as a human can deal with, go from many hundreds of dimensions down to just a few. And then the techniques we've shown here really add information to that. And of course, it's all available in PLS Toolbox and Solo, and the hyperspectral imaging stuff, of course, requires MIA or Solo MIA. And with that, I'd be happy to take any questions. What do we got, Scott?
We had one about the RGB colors, probably when you were adjusting the gun order. Can you change the colors for the PCs in that RBG, or in the three or
Yes.
three slabs?
Yeah. And so you can select any three PCs to display as red, green, blue, and then choose what order you want them to be, which one you want to be which, by changing that color gun order. And depending on how you do that, that might be more sensible for the problem you're looking at.
And if you wanted to change the actual colors from red, green, blue, you can do that too. It's a setting in the plot controls, and I'll look that up here, and I'll post it in the chat. Um, and I was also going to mention, someone asked about recording. Yeah, we're recording this. It'll be available in about a day, and the next data import webinar will be on May 12th, roughly the same time.
Yeah, that'll be a good one to tell you about how to actually bring all this information in so you can use it. And data comes from an awful lot of different places, and it's stored in a whole bunch of different ways. So uh, Lyle is going to take you through a bunch of tricks to make sure you can actually get this into your data set object and use it.
Do we have to register again for the next seminar?
Yes, please.
For the data import, oh, okay, the data import. Someone's asking about importing LCMS data. Yeah, we can put that on our list for the next one. In the webinar from last week, Rasmus displayed spectra with the included variables colored, but the excluded variables displayed in gray. How does one create
Yes.
such a plot? And by
Ah,
default, the excluded data is not plotted.
uh, okay. I could do a really quick example of that if you like. So, yeah, here I can just use this. Product spectra. So this is the spectra of all these foodstuffs near IR. Plot the data, and it looks like this. And let's say that I'm using I'm going to do this. I'm going to select this part and I'll do another selection, and this part, so say those are the parts that I'm using. I'll say edit, include only selection. So I'm just using that. Here's all the data. But what you can do is say view excluded data. And when you do that, it'll show it grayed out eventually. There. Okay. So there it is with the excluded stuff grayed out. Is that what you were looking for?
Yeah, I think that was it.
Okay.
I had another one, in PCA score plot. When there are too many samples, how to see all the sample labels?
Oh,
I think maybe we're talking about declutter there.
right. Um, there's a setting in the plot controls, and I don't know if it'll show this declutter labels, and you can force it to show all the labels. That's when you set it to none. Or decluttering the labels, basically what it does is it removes labels that are on top of each other and it only shows one of them. So uh, that decluttering the labels helps. I will tell you that the one thing that makes the plotting really slow, that seems to be a MATLAB thing, is to have thousands of labels. It doesn't handle the labels very well in terms of memory management and speed management. So it's really useful to only include the ones you want. And so for that, that was why I showed you that trick about just selecting like what samples or what channels maybe that you want labels on, and then putting them just on those, because that really speed things up a lot.
Yeah, I think kind of had a follow-up here is when you selected points to exclude, like you showed on the NIR data set, and you keep the labels on the data points the whole time so you can choose by the label. If I have a number of labels turned on, select one to exclude and the other numbers go away. And I can't tell which one to select next.
Okay, I don't think I can answer that one in real time.
Yeah, that's a little
I'd have to see what you mean on a real plot, I guess.
there um there is the search bar, and that's maybe a little tangential, but you can open up a little bar at the bottom of your plot, that allows you to search by name. Maybe that could help you um,
Yeah,
in the,
and I'm not an expert in the search bar. That would be a Bob thing. So
yeah.
Bob's
If
really an expert in regular expressions and the search bar.
if you search for search bar, you'll see how that functionality works, and that might be able to help you with that. Is there a way to sort loadings ascending or descending?
Uh,
Not exactly sure if I
so you for instance,
understand that.
like if you have yeah, you want to then get yourself a list of say wavelengths in your spectrometer that are ordered by how big the loading was. Um, yeah, I think that's something you'd probably have to export them and do a sort on. That isn't one I've ever been asked for.
Plot controls don't work on contribution plots. Any plans to update this?
Plot controls don't work on.
Contributions.
Oh, yeah, contribution plots are a standalone um, sort of thing, if you will. It generates them and then they're static. You can't change them. So I'm not sure what you'd want to change on that.
So I guess there's no plans to update that, but I guess you could pull the data out and plot it with plot controls.
Yeah, if you actually send us a note on exactly what you want on that, there's a whole bunch of stuff I didn't show, like the variance captured and the contribution plots and the correlation maps, and there's really a ton of things here that I still didn't get to, and I'm running over now. Anything else?
Uh, I think we'll just take this one last one, and then if you really have additional questions, you can just email us. Um, Whoa, the MCR image looks crisp. How can you enhance the images?
Uh, yeah, I Photoshop, I guess. Um, if you want to do post processing, yeah, I'm not exactly sure what all you're asking on that. What you would else you might like to do on it. So um, that's a good question. We haven't implemented like a lot of smoothing or whatever in the score space here on images. That is something that we could do if that's what you're thinking.
Or
So
Neil suggested maybe applying auto contrast. Um, it's the
yeah, I think that's already. Oh, okay. Bingo. Yeah. Um, and and that helps on this. But I don't know if you're looking for when you for smoothing here or what. So
yeah, maybe a post processing thing.
yeah. Mm-hmm.
I had one other request. I would love to see variance contribution plots.
Ah, okay. Are we talking like VARCAP? Is that what we're talking about? I um, well, I will show this, and I don't know if this is exactly what you're looking for, but if we have our loadings plot, so these are the actual 5 components in this system here. But you can actually get a map here of oh, I don't have my original data available for this, so I can't show that. You can show that for loads. Um, quickly here, I'll do PCA on Excedrin real fast here, and I'm gonna pre-process with just mean centering, and I'm gonna make a quick model. And when it pops up, I'm going to turn cross-validation off. And now over here in the loads, I'm not sure if this is what you're looking for, but here are my loadings in this. I can tell definitely that first one has to do with aspirin, but the variance captured plot for this are can be kind of interesting. Did I actually press the button?
Was it taking a long time to generate because it's
A
hard
really
one?
big data set? It might be. This is what happens when I go off piece, so to speak. Yeah, it must be. So you can though get a plot of the uh, variance captured at each wavelength in this. And there it is. Okay, just takes a while to generate. So um, this shows you where in the spectrum the information is captured for each component. This is making my laptop, incidentally, work pretty hard here. I'm just doing this on my laptop. So you could see in that that the first factor in this captures most of the variance. A couple of the latter factors capture things at the higher wavelengths there. And so hopefully that was sort of the one you were looking for.
Okay, I think we're gonna wrap it up here. We're at 8:45.
Yeah.
I was going to mention one other thing that, in case people didn't see it go by in the chat, about naming components. That'll be a feature in our next release, and you can find that in the tools of the analysis window, and they'll be incorporated into the plots where appropriate.
Yeah. Okay. Well, thank you, everybody, for coming. And have a good weekend.
Next release will probably be later this summer. Thanks, everyone.
Okay.